In this video, we continue our discussion of scattering theory with partial wave analysis. We'll start by listing and defining what partial wave analysis is. Then we'll use the localized potential approximation. We'll talk about the radiation and intermediate zone solutions. And finally, we'll lay out how to solve the interaction zone, which is the final step in this partial wave analysis solution. So let's review first our quantum scattering. We have an incident plane wave, which is psi I of z is a times e to the I kz, plane wave in the z direction. And then the scattered wave is a spherical wave, and it looks like some constant, normalization constant b, e to the I kr over r, where k is equal to the square root of 2me over h bar, and this is elastic scattering, so k doesn't change. You just change from a plane wave to a spherical wave from the scattering center. At far points from the scattering center, the solutions must look like the superposition of a plane wave and a spherical wave, and that's what we've written down here. So far away from the center, psi of r and theta, again, this is cylindrically symmetric, so the cylindrical part doesn't matter. The polar angle doesn't make any difference, is a times e to the I kz plus f of theta e to the I kr over r, where f of theta is called the scattering factor, and it depends on the azimuthal angle theta. So the differential cross-section then is given by d of theta, which is d sigma by d omega, and that's equal to the absolute value of f of theta squared. So if we have a spherically symmetric potential, the scattered wave can be separated into a radial portion and spherical harmonics. So we can write our outgoing scattered wave as r of r, capital R, lowercase r, times the spherical harmonics ylm of theta and phi. The modified radial function, u of r, which is equal to r times capital R of r, has to satisfy the usual differential equation, or the Schrödinger equation, which is e times u is equal to minus h bar squared over 2m, d squared u by dr squared, plus v of r, which is our central potential, plus h bar squared over 2m times l plus 1 over r squared, all times u. Now, if you remember from the hydrogen atom, this is exactly what we had from the hydrogen atom that came from the separation of variables from the radial to the angular variables. We got this sort of centripetal term, which goes like 1 over r squared, and it depends on the separation constant, which is L times L plus 1, L being the orbital angular momentum quantum number. For very large values of r, we can assume that the potential, since it's a central potential, goes to 0. And so we can ignore this potential, and this goes to 0, and we can also ignore this potential because it goes like 1 over r squared. So we can neglect, for very large r, we can neglect this potential because it goes to 0, because it's a central force potential. It goes to 0, it's well behaved, and the centrifugal term, the second term from the separation constant, also goes to 0. So the equation simplifies greatly, and it just becomes d squared u dr squared is equal to minus k squared times u. So that's sort of the asymptotic solution. Well, we know what that is. The solution to this is u of r is c e to the I kr plus d e to the minus I kr, which are basically spherical waves, because if you recall, u of r is r times capital R. So capital R is this over r. So it's two spherical waves. The second term, that is the incoming wave coming in the negative r direction, can be ignored. And so d equals to 0. And our final solution then is that r, capital R of r, is proportional to e to the ikr over r, which is in fact a spherical wave. So for a central potential, a spherically symmetric central potential, we have spherical waves outgoing, which is what we had postulated from the beginning. So this is the form that we expect from our physical argument in the k times r is much, much greater than 1 regime, and that's called the radiation zone, when you're far away from the scattering center. So now we can sort of define 3 zones for our so-called localized potential method. We start with the radiation zone. That is very far away from the scattering center. You just have a simple spherical wave solution. In the intermediate region, which is this blue part, we can still assume that V is approximately 0, but we have to include the centrifugal term from the separation of variables, and that's called the intermediate region. And then finally, in the scattering region close to the potential, we can't make any approximations. We have to include the potential, we have to include the centrifugal term, and solve the entire problem exactly. So in the intermediate zone, we know what it looks like, the wave function looks like in the radiation zone. It's a spherical wave. In the intermediate zone, the Schrödinger equation becomes the following. We still can ignore V, but we can't ignore the centrifugal term. So we have d squared u by dr squared minus L times L plus 1 over r squared u is equal to minus k squared u. So the solutions to this are linear combinations of the spherical Hankel functions. And the Hankel functions, just like other functions that we've looked at before, have oscillatory components. And we have a component that gets large at r and one that gets small, that dies away at r. And the Hankel functions, h sub L of 1, the spherical Hankel functions of the first kind, of x is equal to the j sub L of x, which is a Bessel function, plus I times the Neumann function, n sub L of x. And the second kind of Hankel function, so we have the first kind and the other second kind, is j sub L of x minus I times n sub L of x. So you can see these two come in pairs. It's the positive and negative combination of the Bessel and the Neumann functions. Well, as r goes to infinity, what do these look like? Well, this term up here with the Bessel plus I and L goes to a spherical wave going outward. And this one here, when r goes to infinity, goes to a spherical wave moving inward in the negative r direction. So these can match up very nicely with the solutions in the radiation zone, which include an outgoing spherical wave and an incoming spherical wave. But of course, since we're scattering, we don't care about the incoming spherical wave, so we're only going to keep the outgoing wave h sub L, the first kind. So we're only going to deal with this first kind, which is j sub L plus I n sub L of x. So the Hankel function of the first kind, as I said, are combinations of Bessel functions. And we write the Hankel function of the first kind, the h sub 0 of the first kind, is equal to minus I e to the ix over x. And h sub 1 is equal to minus I over x squared minus 1 over x e to the ix. And as you can see, these expand out in powers of 1 over x. So the h2 is minus 3i over x cubed minus 3 over x squared plus I over x times e to the ix. And finally, we can look at what these look like when x is much, much greater than 1. So when x is much, much greater than 1, then you can see that only the last term survives. Because when x is much, much bigger than 1, this term drops off faster towards 0 than this term. these two terms will drop off faster than 0 towards this term. So they all will look like e to the ix over x. But this one has a minus I, e to the ix over x. This one has just a minus e to the ix over x. And this one has plus I, e to the ix over x. So we can, this is L equals 0, this is L equals 1, and L equals 2. And so we can write these in a compact form that when x is much, much greater than 1, the Hankel function of the first kind, sub L, is equal to minus I to the L plus 1 power e to the ix over x. So when L is equal to 0, this gives us to the first power, so we get minus I. When L is equal to 1, you get this squared, which gives us minus 1. When L is equal to 2, you get this to the third power, which gives us plus I. And so all the series of Hankel functions are can be written down in the asymptotic form with this one form here. Now, the real and imaginary parts of the Hankel function, if we look at the details of this, look like this. For L equals 0, L equals 1, L equals 2. So you can see that L equals 0, we have this part, this is the real part, and then we have the imaginary parts, which look like this. So the imaginary part goes to minus infinity. The real part is bounded in all cases. And they look like sinusoids with 1 over x, right? Because when you break this up, you get cosine theta plus I sine theta. And so you get the sinusoidal term and then a bounding function. And the imaginary part, however, blows up in a negative direction because sine goes to 0. All right. What we're now going to do is we're going to solve the scattering problem in the intermediate region. We already know the solution for the radiation zone because that's just a spherical wave. And we know the solutions are Hankel functions of Kr. So U is proportional to R times Hankel function of the first kind sub L of Kr. Then R of R must be the Hankel function sub L of Kr. And we can write now that in this intermediate region, we have a superposition of the incoming plane wave, which is e to the ikz, and then a sum of these radial functions times the appropriate spherical harmonics, and then coefficients c sub Lm. And this is summed over all possible indices L and M. And so this will give us any arbitrary shape function, because these are just arbitrary functions, complete bases summed over infinity. Now, because this potential is spherically symmetric, we don't have any phi dependence, as we saw before. And so that means we can throw out all the terms that have any phi dependence, and that means any terms where m is not equal to 0. So the only terms that we need to deal with are the YL sub L0 terms for the spherical harmonics and the CL0 terms here. So now my sum becomes this: A times the quantity e to the ikz, which is my incident plane wave, times the sum over L, C sub L0, Hankel function sub L of Kr, and then the spherical harmonic YL0 of theta. And now it's just theta because phi has no dependence. The spherical harmonics then are YL0 are simply given by the square root of 2L plus 1 divided by 4 over pi times the associated Laguerre polynomials of cosine theta. Genre polynomials, pardon me. And if we redefine the coefficients in the following way, we take C sub L0 and redefine it as I to the L plus 1 power times K times the square root of 4 pi times 2L plus 1 times A sub L. We can rewrite these in terms of coefficients A sub L. And this gives the following solution. Psi is then equal to A times e to the ikz plus k times the sum from L equals 0 to infinity I to the L plus 1 times 2L plus 1 A sub L H sub L of KR P sub L of cosine theta. Now this is the solution in the intermediate zone. We want to connect this to the radiation zone because we need to have a continuous wave function. Not only the wave function has to be continuous, but the derivative has to be continuous. So we have to match them up together. At large R, what does the Hankel function look like? Well, the Hankel function, we wrote that down before, is just minus I to the L plus 1 e to the ikr over kr. Right? That's the asymptotic limit for the Hankel function. And so we can write at large R, the Hankel function becomes e to the ikr over r. We have a k in the denominator, which cancels the k up here. And so we have a times e to the ikz plus the sum from L equals 0 to infinity of the quantity 2L plus 1, A sub L, P sub L of cosine theta, e to the ikr over r. So now this is a spherical wave in radial spherical wave. And then we have these terms here which come from the spherical harmonics. And the radiation zone form then, recalling that we looked at the radiation zone, we had A times e to the ikz plus f of theta e to the ikr over r. And we can make this comparison directly. And we see e to the ikr over r comes out of the sum. And so f of theta, the scattering factor, is now defined as this sum. The sum of L equals 0 to infinity of 2L plus 1, A sub L, P sub L of cosine theta. And that is our scattering factor. And so that's the solution that we want in the intermediate zone, connected to what we see in the radiation zone. So this is what our scattering factor must be. The differential cross-section then becomes d of theta is f of theta squared. So when we square it, we need a double sum over L and a sum over L prime of 2L plus 1 times 2L prime plus 1 times A sub L star, A sub L prime, P sub L of cosine theta, P sub L prime of cosine theta. And the total cross-section sigma is just the integral of d theta by d omega. And if we look at this sum, when we take the integral of this term here, if we're integrating over theta, we realize that this can be written as follows. If you have an integral from minus 1 to 1, over which you have P sub L of x and P sub L prime of x dx, this is just going to be a delta function. Delta of L times L prime times 2 over 2L plus 1. And so my total cross-section then, with this simplification, becomes 4 pi, because the integral over phi just gives me 2 pi, times the sum of L equals 0 to infinity of 2L plus 1, because L is equal to L prime. There's a factor of 2 here, which gives me 4 pi, times the 2 pi from the phi integral, times the absolute value of A sub L squared, because L prime is equal to L. And so the only terms that survive here out of these sums are where L prime is equal to L because of the relationship of these two functions, the P sub L and the P sub L prime of x. Now finally, the partial wave amplitudes, these factors A here have to be obtained by solving the interaction zone. So the partial wave amplitudes are obtained when you solve the Schrödinger equation exactly in the scattering region, that is the interaction zone, where V is not equal to 0 and the centrifugal term also equals 0. Now, you have to know the potential for that. Let's imagine for V equals 0, we can find out what the general solution is. So if you have no potential at all, then you have the following. Psi is equal to L, the sum over Lm, A sub Lm, Bessel function sub L of Kr, plus B sub Lm times the Neumann function sub L of Kr times the spherical harmonics YLM of theta and phi. Because this is exactly the solution that we have in the intermediate zone. Where the potential is set to zero, is assumed to be 0. Here, if we say the potential is 0, then we have the same solution in the scattering zone as we have in the intermediate zone. The incident particle, of course, is a plane wave, and it's expressed in Cartesian coordinates. And so we can use the so-called Rayleigh formula to convert this. E to the ikz can be rewritten as a sum from L equals 0 to infinity of I to the nth power times 2L plus 1 times a Bessel function J sub L of Kr times P sub L of cosine theta. So this allows us to re-express a plane wave in terms of Bessel functions and these terms that relate to the spherical harmonics. Note here that the Neumann functions can't be used and m equals 0 because of our geometry, so we've ignored the Neumann functions altogether. The full solution then can be written as follows. Psi of Rn theta is equal to A times the sum from L equals 0 to infinity of I sub L, I to the nth power, 2 times 2L plus 1 times the quantity J sub L of Kr plus Ik A sub L, H sub L of Kr, P sub L of cosine theta. And that solution is the one we're going to take forward and calculate the partial wave amplitudes the next time. But for the moment, we'll leave it here.